We're going to work through a number of conceptual questions here related to Newton's laws to try and really apply those three major ideas that really, like I said, provide a foundation for a lot of physics. So the first question here is asking about a trailer that's being towed and why trailers often have their own braking system. We want to explain this in terms of Newton's laws. This really comes down to a first law thing. When the trailer is braking, the truck has an unbalanced force that causes it to come to a stop. And at this point, as we know, stopping is simply a form of accelerating. So we have an unbalanced force acting on the truck, causing it to stop. The trailer, on the other hand, without its own braking system, would have no unbalanced force, and therefore it would want to continue moving into the truck. Now, in reality, for relatively small trailers, that hitch on the back of the truck provides the brakes. But once we get into a bigger trailer that's a little bit heavier, they do typically have their own braking system for that very reason. That the trailer wants to stay in motion, wants to continue moving at a constant velocity because there's no unbalanced force in order to make it stop. So we put a braking system in, and now the trailer can come to a stop as well. All right, the next one, we're thinking about the motion of an object if it has no forces acting on it. And again, this comes down to that first law here. So I have written up here that first law, just to emphasize that unbalanced forces cause acceleration. So if we have no forces acting on the object, that simply means the object is not accelerating. We don't really know much more than that. We can't say for sure that the object is at rest. It could be at rest and not accelerating. It also could be in motion if it was already moving. What we do know is it's not accelerating, so therefore there is no change to the motion of the object. Okay, that's really what acceleration is, right? A change in the motion, so we know the motion is not changing. In the second case, if there's exactly one force acting on the object, we know that the object is accelerating. All right, if we only have one force acting on an object, there is no way for that force to not be unbalanced. There's nothing else to balance it out. All right, so the object is accelerating. We can even say in the direction of that single force. Lastly, for this third one here, if there are exactly three forces acting on an object, really the answer is we don't know. The object could be accelerating if there are unbalanced forces, if overall those forces are unbalanced, or it could be not accelerating if those forces are balanced. So it's pretty easy to think of a situation where the forces are not balanced, right? If all three are going in the same direction, and that would ultimately lead to acceleration. But we could have a situation where maybe there's one big force going one way and two smaller forces, and that could lead to zero acceleration, or maybe it forms a nice little shape like that where all the forces are going out in equal thirds and they all balance each other out. There's lots of options for how we could not be accelerating, but what it comes down to is we don't know for sure one way or the other. Moving on to the next question here, we have a situation where there's a hand pushing two boxes. We want to start thinking about what forces are acting on the hand and on each of the boxes. So I'm going to go ahead and draw my free body diagram for each. I'm going to start with the easy force that we always know, and that's the force of Earth. That's going to be acting on all three objects. I'm also going to have the force of the table acting on both A and B. Next, I know that the hand is pushing on box A, so I'm going to say I have the force of the hand pushing on A, and then in turn, box A pushes on B. That means, if A is pushing on B, that B is going to push back on A, and that also means that box A is going to push back on the hand. Lastly, it says there is friction, so we're going to have a force of friction acting backwards on both A and on B. You probably could make an argument that there's some additional forces acting on the hand, like the arm, but I'm just going to leave it as that for now. So what we want to do is we want to identify which of these forces are equal because of Newton's third law. So those are those equal and opposite pairs where one object pushes on the other pushes back. So the first one I have here is A is pushing on B and B is pushing back on A. So we know those two forces are equal and opposite. So we can say that A on B is equal to the negative of B on A. The other one we have here is that same interaction between A and the hand and A. Those are also a third law pair. And so that's what we have there. There probably are some other forces that are equal. For example, we know these two forces, the table and the earth, are equal. However, they're not equal because of Newton's third law. And we do want to make that distinction, okay, between forces that are equal because of Newton's third law, meaning that they will always be equal, and that's the case with those two pairs, versus forces that happen to be equal, like the force of the table and the force of the earth acting on each box, but are not always going to be equal. Keep in mind that third law pairs act on different objects, and so we see that the one pair, all right, one force is acting on the hand, the other is acting on box A, and for the other pair, one force is acting on box A, the other is acting on box B. We'll never have a third law pair where the forces are acting on the same object. It's always shared between two objects. All right, moving on to our next one here. You're standing on a frictionless surface in a vacuum next to a box, and you push the box. Describe the motion of the box during the push and after the push. Describe your motion during the push and after the push. So for the box, during the push, we're going to have that box is going to be speeding up because we have an unbalanced force acting on it. After the push, we take away that unbalanced force, and that means that it will travel with constant velocity because there's no longer an unbalanced force acting on it. For B, describe your motion during the push and after the push. Well, during the push, it's going to be the same idea. Okay, we're going to be speeding up during the push. This really results from two things. Number one, because of the third law, there's an equal force back on you, and that happens to be an unbalanced force, which causes you to accelerate. Same thing as for the box after the push. We're going to have a situation where we have no acceleration, meaning a constant velocity, and that results from the lack of an unbalanced force. All right, moving on to the next one here. We have two forces act on box A as shown. Forces are drawn to scale, and we first want to know what is the direction of the acceleration of box A. Well, we can clearly see that there's more force to the left than there is to the right. So we have an unbalanced force going to the left, which means we must be accelerating towards the left. Question 2, which way is box A moving? Okay, this one's a little bit tricky here, but you might be tempted to say that it's moving to the left, but keep in mind that accelerating and moving are two different things. We can't determine which way it's moving simply from the forces. We can only determine the direction of the acceleration. So, the next question, could box A be moving to the left? Let's think about that for a second. If our velocity was also to the left, what would that mean? Well, that simply would mean that it was speeding up. So it could be moving to the left if it was speeding up, could be moving to the right. That's also possible. If instead our velocity was to the right, that would mean that the box was simply slowing down. And then lastly, could box A be moving at a constant speed? This one is no. It must be accelerating because we have an unbalanced force acting on it. Moving on to this next question here, similar one, kind of working backwards here. So we're told the motion of the object, and we want to think about what forces would allow that to happen. So in the first one, we want an object B, to be traveling to the left and be speeding up. All right, so we know our velocity is going that way. If we're speeding up, that means our acceleration must also be going that way. So our unbalanced force has to be to the left. That means there are two options. We could either have a second force going to the left, or, okay, I'm going to draw my other one in green here, we also could have a force going to the right, but just smaller. So either one of those options would be valid. The key is we want to just have an unbalanced force to the left. Second one, traveling to the right at a constant speed. That's going to mean that our acceleration is 0, all right, and our velocity is to the right, as it says. So how is that possible? Well, that's only possible if our force is the same amount, but going to the left. So those two forces, in this case, would be equal. For the last one, we want to travel to the right and slow down. So our velocity, once again, is going to be going to the right. Our acceleration must be going to the left because we're slowing down. So much like the first one, we either can have an additional force going to the left, or we could have a smaller force going to the right. So any force going to the left would work, because then our unbalanced force would be to the left, and that would cause us to slow down. Or we could have a smaller force going to the right, and then once again our unbalanced force would be to the left, and that would cause us to slow down. Moving on to our last conceptual question. This one actually gets a little bit into some of those algebraic ones. But we have a horizontal force with a magnitude of F accelerates object A that has a mass of M. How much force should be given to objects B and C to give them the same acceleration? B has a mass of 3m, C has a mass of 2/3 m. So we could think about this conceptually, to an extent at least, and we're thinking about our equation here, sum of the forces equals ma. So if we think about the forces acting on this object, we're going to have the force of the table that these objects are sitting on, the force of the earth, obviously, okay, and then we're going to have this force of the push, okay, or whatever is making these objects accelerate. In this situation, that force, that is the net force, or the unbalanced force, okay. The reason why I point that out is in this equation here, sum of the forces, that's really another way of saying the net force. Find the amount of unbalanced force. And in this case, whatever force is going to the right, that is going to be your unbalanced force. So, some people will look at this problem and realize that this mass is 3m, so we need 3 times as much force because mass and force are directly proportional. And this mass is 2/3 m, so we need 2/3 as much force because, once again, mass and force are directly proportional. However, we are going to learn the algebraic setting up multiple equations way of doing that. So if we set up this equation for object A, we're going to say that F is equal to ma. We know F is this force here, all right, this being exerted on A, and A has a mass of m. For object B, we're going to say that FB, the force exerted on B, is equal to 3ma. All right, and for C, we're going to say that FC is equal to 2/3 ma. What I would look at, the really easy way to substitute here, is that ma shows up in both of these equations. That ma is simply equal to F. So I can say that FB is equal to 3F, and I can say that FC is equal to 2/3 F. So that's a relatively easy way of solving it. There are others, as there always are, and so if you did a little bit more algebra to solve it, that's perfectly okay. But there is that relatively quick shortcut to solve it. Alright, so moving on to the second question here. Once in motion, 3 boxes move at a constant velocity. A force of the magnitude of F2 acts on A in order to keep it moving at a constant speed. How much force should be exerted on B and C? This is one of those questions where you're probably going to be annoyed at me. Maybe some of you are a little bit confused as you're reading it. I guess in some ways it's a bit of a trick question, but no force is needed to keep an object moving at a constant speed. So what that really means is this F2 that we're defining is equal to 0, and that's also equal to the force exerted on object B during this time, call it FB2, and the force exerted on object C, FC2. All of those forces are going to be equal to 0 because we don't need a force to make an object move at a constant speed.